Good morning, everyone. We'll wait a few minutes for other folks to join us, and there are people who are joining us directly through LinkedIn who haven't. So we have two options. One is through the Zoom introduction, and the other is through LinkedIn directly, and we cast through LinkedIn, for which many people have signed up. So you may not see them on the Zoom call, but they'll be there at LinkedIn. So we're just going to wait for some more people to join us. Give us a few minutes, and we'll get started. All right. Well, we're keeping in respect for everyone's time, we will now get started. And other people will join as and when they join. So first thing, I wanted to welcome you to our webinar this morning. This is the second in a series of 7, and each of them is titled 7 Reasons, 7 Considerations, etc. And so I wanted to thank you all for being here. I know that everyone is busy and making time to learn something and to be present, to take in new technologies or new tools that can help you, require some investment of your time and effort. And I acknowledge you for that and appreciate it. I want to thank you and let you know that it's a valuable choice of time, because my commitment is that you come away with something of value today that you can apply right away to improve your processes and get benefit out of what you learned today. Okay, so it's very practical. It's very simple webinar, and we will be here. Should you have questions that are of a confidential nature, reach out to us afterwards, and we can schedule a one-on-one. Okay, sign a CDA if necessary. So without further ado, I'll get started. So the webinar today is titled 7 Reasons to Consider Scale Up with Radial Flow Columns for your ion exchange affinity or HIC separations. Now this is radial flow chromatography. For some of you might be new, but for many of you, it's a technology that has been around for a while now, and it is established and it's proven. So for some of you who will start to use it now, you get the benefit of years of experience and success that other people have had. So before we do that, a little bit about Sepragen, who we are. So we are a company with a 30-year-old history. We have 16 patents, many more in the process of being filed. Our products, particularly these radial flow columns that I'm going to talk about today, are today used in 30 plus FDA-approved drugs. Okay, so these are commercially approved drugs. So if you have questions like whether it's scalable, whether it can be used for GMP, those can all be put to bed right here. So they've been used on 30 plus FDA-approved drugs so the regulators know about this technology, and they are in many CMCs, okay? And there are 200 global installations, so it's not like it's in India or it's China or it's in Europe. It's on 4 continents around the world, okay? And our products are used in 2 major approved COVID-19 vaccines. Not some people who are developing a vaccine in the lab, but these are vaccines that have been administered to over 100 million people. So our current products are used in the production of $20 billion worth of biological drugs and vaccines. We provided equipment, some very novel equipment for high throughput, large scale manufacture of COVID-19 vaccines, and at a very important time in our history during the Delta wave, and we delivered these in 14 to 18 weeks, okay? So as a company, we are inventors of radial flow chromatography. We are innovators, and our products are used to reduce time to market, to reduce infrastructure costs, cost of goods, and improve workflow. We are inventors of radial flow chromatography, QuantaSep chromatography systems and skids, whole line of them, single-use chromatography systems and skids, continuous 2 and 3 column systems, buffer dilution, buffer blending systems, and integrated, first in the world to do integrated and intensified chromatography. And what that means is on the chrome system itself, you can do buffer blending as well, right? So you don't have to do buffers, and we can integrate many unit operations on a single skid. These are some of our customers, many of which are using our products for commercial manufacturing, but we can't talk about each particular applications because of confidentiality reasons. And there's a quick glimpse in a picture of our high productivity solutions. We are here to talk about radial flow columns and why you should use those. And those are on the right here. But we have chromatography systems from the bench to large scale. And then we also have continuous 2 and 3 column single-use chromatography systems with inline buffer blending, which means you can make stock concentrates and do chromatography at the same time, single-use systems, automated packing systems. So lots of other things. But today our focus is why you should use radial flow chromatography. So what is the problem with chromatography scale-up? Why should you consider radial flow chromatography? Okay, if something may be working for you, maybe it is working, maybe you know it's working, or maybe you don't know what's missing, right? Many times, I wear glasses sometimes and there's a little speck on my glass. Initially, I notice it, but after a while, my eyes get used to it and I don't notice that little speck, right? So it's like that. People get used to a certain technology, they just go with it, but they don't realize what they're missing. So I think today you get an opportunity, if you're not familiar, to see what you might be missing. And I think that's where you can really improve your game. You have masters like, if you follow basketball, like like Steph Curry, for instance. And after each game, Steph Curry looks at the video of his game, right? Not to see what's wrong, but really to see what's missing, because that gives him the clue of how he can improve his game and take it to the next level so he can go from one championship to another. So I think investigating what's really missing and what you're doing is really a good exercise if you are to improve your process, if you are to improve your game, and you are to bring more productivity enhancements to what you're doing, okay? So the 7 reasons to consider radial flow columns. The first one is throughput and pressure problems with conventional chromatography columns. Very often upon scale up, you find that you cannot go faster with axial columns. You're running a 20-centimeter bed. You may have done your separation of little high trap columns, but when you go to scale up the certain buffers, you get high pressure. You try to go faster, you get high pressures. You have to slow your process down, change your columns, increase your volume, increase the diameter, and it's a mess, right? You're optimizing things on the fly on a large scale. So what can radial flow columns do? We'll assess that. And then how about scale up itself? Everyone says scale up with axial conventional columns is easy. As some people say, keep the bed height constant, increase the area. Other people say, keep residence time constant. Well, which is it? And what are the consequences of doing what you're doing? Why not one simple rule when you scale up? Well, that's what you can get with radial flow columns. You're doing clinical runs, making antibodies for clinical production. Often you do, a campaign or two. Then you put the columns away and put the resin away and may not come back to it for 2 or 3 years. Huge amount of investment and wastage of resin. So does the column have anything to do with it? Absolutely, and we'll examine that. Could the radial flow column actually have you save significant amounts of expensive resin? You bet. And we will take a look at that. Okay, so stay tuned. And then what about if the titers are going up in cell culture, right? You started off when you built your facility, you were at 0.5 gram, maybe 1 gram, a liter titer. And now you've got great cell lines. Your upstream guys are all happy. They're doing 5 grams a liter, 6 grams a liter, 8 grams a liter. Well, the monkey is now on the backs of the downstream process. That's a bottleneck. But the downstream suites are small, right? They were designed for when the titers were low. So now what do you have to do to address that? How do you get more space? Do you build a new facility? Do you tear down walls? Do you hire more people, do more cycles? Right? That's the conundrum we find ourselves in. We'll address that. And what can radial flow columns do about that? And then what about capacity utilization? When you go to larger and larger columns, it's easy to say, well, make the column wider. Well, all your development work is done in little columns like that. But now you go to 1.5 meter column, and the capacities of the resin is not the same. Okay, you maybe people say, I'll operate at 80% of the theoretical capacity. Push it to maybe 85%. Because, in packing, there are variations, etc. You've got a lot of money tied up in resins in the process, and you're taking 10, 15% off the top because of inefficiencies on how the column is packed and the capacity utilization of that column. What can radial flow columns do about that? Simple, easy, automated packing. Packing can be a nightmare with large columns. Small columns, yeah, no problem. 10 centimeters, 20 centimeters. You're going to 60 centimeters, 1.4 meter columns, 2 meter columns, yeah. That's when you first confront that column packing is not reproducible. What can radial flow columns, can they help you with that? Yes. And then, are you actually taking a risk by switching if you decide to switch to radial flow columns? And what if your process is already in phase 2 or phase 3 or approved, and you're encountering those problems? Can you switch to radial flow columns? Is there relief for you? And the answer again is yes. So stay tuned. So this is a typical ad hoc response to, significant scale up. Get bigger, wider columns, more space, more cycles, FTEs, more buffer, long cycle times, more headcount, more documentation, more training, more infrastructure, more of the same. And that just multiplies the headaches, probably not additively, but several in several ways, right? Because not only are your process size of the equipment increased, but your infrastructure has to hold out as well. So what are radial flow columns, right? This is a low-hanging fruit. It's a change, it's a small change anyone can make in their process without affecting their CMC. Because you're not changing the resin, you're not changing the buffer, you're simply changing the operating conditions and running faster with lower back pressures, and that's it. So it's a really inexpensive, low-hanging fruit to intensify your process, speed it up, reduce your cycle time, and reduce costs. How do these columns work? Well, if you look at a radial conventional column, you look at this picture, the flow in a conventional column is applied to the top of the column, just like here, except there's a circular frit on the top, right? So there's a circular frit on the top, circular frit on the bottom, and in between the frit sandwich is resin, right? So the flow comes into the top, gets distributed by the top frit, goes through the resin bed, and comes out the bottom. Well, so if those columns become bigger and taller, you have back pressure problems. If they become wider, you have distribution problems. Right? You have space constraints. You have resin capacity problems. You may have channeling in the bed. In radial flow columns, in this design, you'll see that there is a concentric frit on the outside of the column. So just inside the tube, the outer wall of the column of the tube, excuse me, there is an outer frit and there's a cylindrical inner frit. So concentric cylindrical frits. And the resin is held between these two frits, right? And inside the inner frit is a space holder or a blank or an empty cylinder. So the flow comes in now and gets distributed to the entire outside wall of the column and then travels radially in through the resin bed, through the inner filter, and slides down the side of the space holding cylinder and out the bottom. So what do you have? You have a very large area over which you're applying your flow, which is the 2 pi r h, as opposed to the pi r squared in a traditional column. And then you have a very short bed length. And the bed height in this case is the radial distance between the outer and the inner frit, right? So you have a very short bed height. You have very large areas. So if you take the area and multiply it by the linear velocity, if the area is large for the same linear velocity, you get very high flow rates. Because the bed length is short, you have very low back pressures. Scale up of the column is easy. You simply make the column taller, right? So if you double the height of the column, you've got double the area over which you apply a flow. You've got double the capacity of the resin, so you can load twice as much, double the area, so you can flow twice as fast. And because the bed height, which is this radial distance between the two frits, has not changed, the back pressure remains the same, right? So, and then your elution time remains the same. So it's very simple, and simple in theory, simple in practice, okay? So this is one of the problems with throughput and pressures are very, very common problems with conventional chromatography columns. And so what can radial flow columns do? Well, the problem, of course, with axial columns is that you have high operating pressure, because very often, even in a high trap column, somebody can do an ion exchange or HIC or affinity separation, but the manufacturers say, well, if you're going to run it at production, have a 20 centimeter bed. But what's the reason for the 20 centimeter bed? Well, we don't have a reason. But that gives you a good residence time. Oh, okay, so you scale up with equal residence time? No. But you keep the bed height the same. Okay? So no, there's no rationale. The fact of the matter is that with membrane separations, which have next to no bed height, you can get adequate ion exchange. You're going to get adequate bind and elute separations, affinity ion exchange, like that. So for traditional separations like size exclusion, yeah, you need bed height, you need your traditional resolution, giving given by the Van Diepter plot, but not for ion exchanges of affinity. It's strictly residence time dependent. And then, of course, you have some resins which are soft. So if you pack them in large columns, then you try to run fast, you have resin or bed compaction. And then, of course, you have limited suites, right? So if the titers are going up and you have narrow space, well, then you don't have enough space. So what do people do? They say, well, we'll use the same column. Oh, we have this column lying around. We can use it instead of 10 centimeter. Well, I'm going to use a 20 centimeter, pack it slightly higher, maybe 30. That's fine. So then you run into problems of overpressure. Or if they say, well, we have this other big, large column lying around, let's use that. Now you've got distribution problems, uneven flow distribution, channeling. And then packing these columns is unwieldy and requires, big packing scale. So overall purification costs today are downstream processing costs are higher than upstream costs and account for majority of the costs of a biological process. And column is the dumb end of chromatography. People say that the smart sign the resin. Well, if you don't have the right column, it takes all the performance out of the resin and compromises your resin performance. So here's a short video that I'd like to share with you about radial flow columns.
Welcome to our series of
Which has
tutorial
been put
videos
out by
from INL Biosystems. Today we will present the principles and benefits of Sepragen's Superflow Radial Flow Column. To explore the key benefits of this technology, we need to observe the fundamental differences in design and flow physics of the radial flow column. Unlike a traditional axial column, the sample is applied along the outer wall between the outer column frit and column body. The outer frit contains one or two porous concentric cylinders. The eluent and the sample will enter the chromatographic bed through the outer frit and travel through the column horizontally. It is then collected inside the inner frit and eluted through the bottom outlet. Using the Superflow radial flow technology, the bed height is calculated as the distance between the outer and inner frit. Superflow's radial flow column drastically increases your productivity, helping you reduce your bottlenecks in biochromatography. The radial flow's unique design offers a significantly larger sample inlet area. Even at higher overall flow rates, the column's radial design results in lower linear velocities, which increase the interactions between the sample and the resin, resulting in higher quality separations without compromise. An additional intrinsic design of the Superflow column is the simplicity of linear upscaling from the lab to production scale. As the system pressure does not increase with the column size, this eliminates the complexities of linear upscaling, resulting in data from a small scale that is more representative of what can be achieved at the larger scale. Wouldn't it be nice to accurately predict what a 350 litre column behaves like before spending €250,000? Our wedge column represents a cut-out version of a much larger column to explore processes before scaling to production size. The Superflow columns are available from 50 millilitres both in acrylic and stainless steel up to 500 litre industrial production ranges, with the flexibility and engineering services to accommodate custom builds and special projects. Superflow represents a superior technology for applications such as affinity and ion exchange chromatography. This is complemented with the simplest packing protocol of any column commercially available on the market.
I'm just going to move on to, I'm going to pause the share, escape this. I'm going to move on to the next slide here. So that gives you a visual of the radial flow column. We've got videos demonstrating packing of those columns, running of those columns with automated systems and the like. But with that said, I wanted to move on. The columns are used today in all kinds of applications, from recombinant biosimilars, where people are looking at lowering costs, vaccine production, manufacture of antibodies, human plasma proteins, oligos and peptides, viral vectors, proteins for infant formula, cell-based foods, precision fermentation, proteins derived from precision fermentation, and proteins, particularly antibodies for animal health. Okay, so I think we showed you in the video how with conventional columns, which have a very small surface area versus radial flow columns and large bed heights, how you can go to much larger area and smaller bed height radial flow columns. Also, the flow distribution of radial flow columns is much better than conventional columns. See, in conventional columns, when you scale up by increasing the bed and keeping the bed height constant and making the column wider, well, your small columns don't really model for that, because the distance, see, in a small column, the distance y is the bed height, and the distance x, which is going to the edge of the column, going down and coming back, part of the flow goes down the center, part of the flow goes to the outer edge, comes down and goes through. You can see that the distance that the flow travels in a wide axial column along the X or B flow path, right, or A flow path is 2x, x plus y. And if it's going down the center of the column, it just goes a different distance y. So you have a parabolic flow profile, and so you have early breakthrough in the center of the column compared to the edge of the column. So you don't really utilize this capacity at the edge of the column with conventional columns as you make them wider and wider. And also, when you're cleaning the column, you clean out the center of the column first and the edges later. So you have widening, peak widening as a result of that, and increased buffer consumption and poor utilization of the resin or media. Now, in radial columns, of course, the area is still this pi r squared is 2 pi r h. So the areas are much bigger. And so for the same linear velocity, the volumetric flow rate is much higher. And because the bed heights are very small, the back pressures are much lower. So we have columns going, the operational columns, to 300 odd liters, 350 liters. And, and we are looking at 400 and 500 liters for certain high-value dairy applications for infant formula. And these columns are all can be automated and packed in the same amount of time, which is under an hour, as we do with small lab columns. And by the way, I think the video said that the columns can go down to 50 ml. Well, we have 5 ml columns now that people can use on their current process development systems to start developing processes on radial flow columns, do viral, viral validation studies, whatever other studies they need to do at a small scale, right? And then for large scale, we have automated packing systems as well. So it's very simple and easy and reproducible to pack the columns and have all the data according to 21 CFR Part 11 compliant, fully GMP. These systems can be networked to your system for download of data. You have recipes for different resins for packing different columns. So quick, I'll share with you some examples. Below is an example of a conventional separation on an axial column. Okay, that was scaled up about 5-fold onto a small lab radial flow column. And the process it's a 5-fold scale up, but the process was 3 times faster. Not 3 times faster at the scale, but assuming that we had scaled up an axial column 5 times, whatever that flow rate would have been, the radial flow column delivered 3x faster with the same performance. And here on the right is a fast protein A, standard, I think MapSelect Sure type resin, 250 ml column. And these, by the way, are pre-packed with the resin. So you can talk to us about pre-packing the columns with resin. So you don't have to even learn how to pack the column. We'll provide that as a service. This one was running at 100 mils a minute, 4 grams tighter, loading 1.75 liters, 7 grams, 92% recovery, and the cycle time was 45 minutes. So under an hour, the entire process, right? Normally it's several hours. So even in R&D, even in development, people love using the client of ours that loves using these columns because they said, hey, if I'm going through a whole bunch of, different variations of my cells and I'm trying to understand which one to pick, I have only so many machines and so many people, and I'm screening for so many different variants. Well, on small screening columns, robot-type columns, there's not much I can find. So I need to make enough material so I can do some proper studies. And with radial flow columns, if we can do this under an hour, we've got, my department has twice or 3 times the productivity, and we can do more work, right? Instead of people standing in front of a column, watching it for a day, doing separations and tying up my chromatography systems for that long. So it's a high productivity solution, whether it's in manufacturing or a pilot plant or even in development. Here's another example of an enzyme separation on ion exchange. This process was developed on a conventional column, lab column here on the left. And so on an ion exchange, that's the load, that's the elution peak. And the black line here is simply they've taken samples and plotted out the activity of that particular enzyme. And the peak, of course, the product was eluted by a linear gradient, okay, on a conventional column. Well, they ran the same thing, scaled it up about 2-fold in the pilot, 12-fold in the pilot plant, and they ran the same separation. You can see it's a double hump peak again. They ran a gradient, so yes, you can run gradients on radial flow columns. But look at the activity peak. Look at the black line, it's double. So it turns out when they did the examination, the product was not stable, right? So it was getting chewed up. And so the faster you could get the product off the column, the higher the activity. They would never have known that had they just looked at their lab conventional data, that simply by speeding the process, they could get higher actual active product. So in many instances, that's a benefit, right? So you can, if you have slow processes, you can have more non-specific binding and impure product coming out. If your product is unstable, again, you lose your product if it's sitting a long time, or separation's taking a long time. So those kinds of things now can be eliminated by simply using radial flow columns. Now so that's the first reason, right? Flow and pressure. And the second reason is, scalability. Well, I talked about this a little bit. What is the right way to scale up? Do you keep the bed height the same and increase, you increase the diameter? Well, you keep the bed height the same, keep the same back pressure, keep the same linear velocity, and the same bed height equals the same residence time. But in reality, both vary. Separations can be easily developed on 3.5 centimeter high trap columns. The same separation later is developed on a 10 to 15 centimeter column, bed height column. And then it's scaled up in a pilot plant to 20 centimeter columns running at 300 centimeters per hour or 5-minute residence time. The fact of the matter is that we have done separations with 1-minute residence time and 2-minute residence time. So you can go much faster and you can do keep the same residence time on a lab radial flow column and the same residence time on a large column. You get precisely the same separation, the same back pressure, and the same proportional flow rate, and the same elution time, the same cycle time. Right? So this is what we are talking about here. How do you scale up on a radial flow column? You keep the residence time constant. So, on a small 100 mil radial flow column, you could be running at 40 mils a minute. When you scale up to 75-liter column, you're running at 30 liters a minute. Okay, it's not so simple on a conventional column. And of course, Sepragen provides you with columns at each scale. We in fact provide you, sometimes our columns run fast and people ask us, well, I'm running so fast on your radial flow columns that my current system from another vendor can't handle the flow rates. I'm getting back pressure because my system has flow restrictors in it, or it doesn't have that capacity. So we support you all the way fully, and we have automated systems that can be used with other people's columns, certainly no problem. The radial flow columns can be used with any vendor's resin, so that's not an issue. You don't have to change resins, you don't have to change systems. But should you need it, we can provide you with systems for any scale of our columns, from advanced to large scale. Okay, so we have columns, we have systems going down to 0 to 100 mils a minute, and we have systems going up to 170 liters a minute. Okay, so some of the largest systems in the industry. So we support the scale up effort. That's what we are skilled at. That's what we do very well and have a lot of experience with. The video also showed you what a wedge column is, and it's really the slice. So a scaled down version of a large radial flow column is a slice, just like the slice of your favorite food. It might be cake or it might be pizza. But here's the separation done on a 400 mil wedge column, scaled up 34 to a 12-liter radial flow column. You can see separation times, the elution profile, virtually identical. So from these little wedge columns, we have a 5 mil wedge column as well. So from these little wedge columns all the way to these large radial flow columns, seamless one-step integration and scalability. So no change in pressure drop, and the flow rate can be seamlessly increased in proportion to the scale. And the separation time, the cycle time is the same. So here's that example that we had shared with you earlier, and it speaks to the same thing on scalability. Now, reason number 3, why would you use radial flow columns? Well, I had said in the beginning that you could actually save a tremendous amount of money on expensive resin costs like protein A resin. Well, how can you do that? Well, if we are running 4 times faster, and we've already shown you data for that, and we'll show you more, then instead of using, say, in a traditional case, here's the test case from an actual customer. They had an axial flow column, 40-liter column. Okay, so this was in clinical phase, late stage clinical. They are making large quantities of antibody for clinical process. They had a 40-liter column. This step was taking them 1 day. And this is old data now. So that was $800,000 of protein A, which by today's standard is double that price. Okay, and the CapEx for the equipment and the system was over $350,000, which again, it could be close to double that today. Now, they decided that was taking them 8 hours. They could go to a radial flow column, and the cycle time was, like you saw, for antibody is actually less than an hour. They were a little more conservative, so it took them 2 hours. But they said, look, still in the 8 hours, we'll run 4 cycles. In the 8 hours, we are done. Okay, so instead of a 40-liter column, they used a 10-liter column, cut down their protein A cost by a factor of 4. So from 800,000 to 200,000. And with a smaller column and a smaller system from Sepragen, the CapEx was also much lower. Now, in a production operation, this wouldn't work because you would run your resin to exhaustion. But for clinical use, you're never going to run your resin to exhaustion. After, a couple of campaigns, it's just sit there and it's a waste of money. So here, you've actually reduced tangible expenses of expensive resin, and you've done the same work with 10 liters of resin instead of 40, okay? Now you might say, some of you may be thinking, well, if you can go so fast through the radial flow columns, what happens to the dynamic binding, because the manufacturers are telling us, well, 300 centimeters per hour, that's pretty good, but, now it comes down to 5-minute residence time. What if I'm running at 2-minute or 1-minute residence time? Well, people use old rules of thumb, right? The fact of the matter is that the resins today have improved dramatically over what they were years ago. Years ago, the dynamic binding capacity curve was, so dynamic binding versus residence time capacity curves were very steep, meaning that if you had long residence time, the capacity was high. If you shortened the residence time, then your capacities were dramatically lower. Today, and that's because the binding sites were located inside the bead, and it took time for the protein molecules to diffuse into the bead and come out. The mass transfer limitations are very high. Today, the grafting is done like little bushes on a bead, right? And the sites are outside, so the exchange of the protein binding to the ligand site is very fast. And therefore, if you look at the current curves of residence time versus dynamic binding capacity, you'll see that going from 8-minute to 2-minute residence time, you hardly lose about 5% or so, 7% of the capacity. You have a 4x improvement in throughput, and you lose 7% capacity. Who cares, right? Maybe on a small scale, R&D folks might care because, I don't have enough sample and all that. But that's not the constraint that should really drive manufacturing, right? Because in manufacturing, particularly antibodies, you have overexpression. You got 5 grams per liter, 10 grams per liter. So the name of the game really is, if you can go 4x faster, you can use a column instead of that 40-liter or 10-liter column. So if your capacity drops by 10%, instead of a 10-liter column, use an 11-liter column. You still save tons of resin. You still reduce your cycle time tremendously. So you cannot blanket say there is a trade-off, but it's not a proportional trade-off. The trade-off in terms of benefit is 90% or 80% compared to the loss that might be 5 or 10%. So in terms of smart processing, it's a great trade-off to take and switch to radial flow columns. Here's data from Genentech, which they presented a paper on. It's not our data, which shows with conventional columns, and this is a kilo scale run. Okay, this is not a bench scale run. Over a 9-month study with axial flow chromatography or traditional chromatography, that process is taking 8 hours. And with radial flow, they were able to do it in 2 hours. And all the product, many runs were made. They've taken out the actual numbers, but you can see that product quality-wise, all attributes were met. Okay, so product recovery, monomer, HCP, DNA, leach protein A, were all within the same acceptable tolerance level that they got with axial columns. So isn't it a low-hanging fruit just to go change the column, don't change the resin, any other condition, you go 4 times faster. It's a no-brainer. Okay, you saw that column. That's a 100-liter column. That's the equivalent of a 1.4-meter column. Okay. So now, as the titers have gone up, what happens in the DSP suite? Well, if you look, this is just a model or plan of a facility. Okay, there are many plans of different facilities, but this is a very common one where at the bottom you have the seed train, you've got USB, turn the corner to DSP1, DSP2, the downstream suites, and to buffer blending here, column packing like that. And you have 2 corridors, right? So the titers go up here, what happens? The DSP suites get stressed. You don't have enough space there Because now what's going to happen? The column sizes are going to become bigger. The skids are going to become bigger. The amount of buffers that you need are going to become a lot more. So what's going to happen? You're going to have this corridor lined with buffers, right? And you don't have enough space. So we have remarkable solutions for these bottlenecks. One of them certainly is the radial flow column, because you're going taller, you're not going wider, right? And we have very compact skids. So in the same facility, without having to break down walls or add more columns, you can get the same, you can increase your production fourfold without really doing anything or asking for a new facility, right? For higher throughput and higher capacity. So one is smart, and radial flow column is a low-hanging fruit, which will allow you to do that, right? Utilize your space, downstream space, DSP suite space much better. And we talked about the capacity of the resin. See, we'd shown you how the flow takes place in conventional columns. Now, if you look at the radial flow columns, you know that 2x plus y that I showed you? Well, in a radial flow column, what happens? The flow comes in, goes a distance x, comes back, goes a distance, comes back, goes a distance, it gets distributed, and either goes a distance x plus y or a distance y plus x. So regardless of which direction is flowing through the bed, the total distance that the flow travels is x plus y, regardless of how big the column is. Okay? So that means that you have a more predictable separation, and the smaller models of radial flow columns work on the same principle as a large column. That's not the case in an axial column where you have the 2x plus y. So if the diameter of the column is small, the x is small and the y is large. But if the column is very large, then you have, a large, the 2x is large compared to the y. So now you have an issue, right? Here, regardless of what it is, the x plus y is always the same. And so as these things are scaled up, this is an example of a separation. This is an approved drug, by the way. So Novartis, been approved for the last 10 years. And when they decided to switch from a conventional to a radial flow column, the scale was at a 20-liter scale with, I think it's a copper chelating resin. They were running soft resin running at 100 centimeters per hour, which is 0.16 bed volume a minute. And the separation was taking them 3 shifts. Okay, the protein binding capacity was 5.3 mg per mil, essentially. And when they moved, so the manufacturing guy wanted to switch to radial flow because they wanted the entire process to be done in one shift. They'd had several problems with the night shift in terms of loss of batches. And he didn't want to incur that. But initially, this was 15, 20 years ago. Actually, more than 20 years ago. The folks in their CMC and regulatory were scared of making the change in phase 2. But then when we talked to them, we said, listen, it's a hardware change. The resin is the same. The elution conditions are all the same. You're just going faster. So we mark these on a small column, and we'll do the same thing on a larger column, and you check the parameters. Should be able to do 3 reproducible runs and run it. They did. Today, this is an approved process that runs on an 80-liter column and has been approved for the last, 15 years, 10 years, something like that. But they were able to do the entire process in one shift. You can see the protein binding capacity also was significantly higher, right? That's because of the distribution that we talked about. So this was one of our earlier examples of changing from conventional to radial flow column and at later stage clinicals. Since then, today we are doing a plant which will be the largest insulin plant in Asia, where it's a post-approval change that they're making to an existing, well-established conventional insulin process. and moving it on to radial flow. The other example, of course, the other reason for making the switch is the columns are reproducible and the process can be automated, whether it's small scale or large scale. People can pack those columns manually. They can pack it in an automated way. They can store all the data. They can have different recipes for different columns and different resins, right? And they can check the HE, and checking the column is the same. Check the HETP and asymmetry, and they're all within the bounds that are acceptable in this industry. And here's a simple example for packing a wedge manually. And on the left panel, you see how you pack a radial flow column. You initially fill up from the bottom, displace the air out, then pack the slurry to the two packing ports into this annular chamber between the two frits. You don't have a frit on the top that blocks the resin from going in. So you can just pump the resin slurry in, and the resin gets trapped between these two frits. The excess buffer comes out until the column packing pressure rises, and then you close the packing ports, and you can stabilize the bed by running in the forward and reverse direction and check the HETP and asymmetry. And here, for instance, you see initially with the wedge, with just a syringe, you can pump and buffer, get rid of the air, prime this little wedge column, then push in the slurry, and you can see the pressure rises. Okay, once the pressure has risen to the level of compaction that you want for your resin, then you can close the two ports and you can run the column in the forward and reverse direction, check for HETP and asymmetry, and you find, within the bounds, whether it's 0.8 to 1.6 asymmetry, that's what you're going to get, right? So reason number 7 is that this is a technology that is proven. So you may not have used it or heard of it, and that's always a little scary, but it's out there and it's proven. The regulators know that. People have huge investments in multi-billion-dollar drugs using these. So it's time for some of you to try these out. And it's been proven in 30 FDA-approved drugs, recombinant proteins, human plasma, mAbs, vaccines, viral vectors, biosimilars, nutritional proteins. And of course, there are smaller columns in use, right? But the point of showing you these large columns is that it's used these are radial flow columns, by the way. Here you have a factory with 4 radial flow columns running in parallel, processing over 20,000 liters of human plasma. There's a factor 8 column. There's a dairy column where you're removing lactoferrin for infant formula on a large scale. We have 1 million liters in the infant formula area. We have 1 million liters of skim milk going through radial flow columns, isolating lactoferrin. We have a 34-ton plant doing that. Okay, 98, 99% purity. Very, very large. And then, like I said, today we have the largest insulin plant going up in Asia using radial flow columns. So here it is. These large skids, and these skids have buffer dilution capability, so reduces the buffer, 125 liter a minute skids, reduces the buffer requirements from 60,000 to 20,000 liters. Radial flow columns that actually are running 3 times faster and remove a major bottleneck in the process, in the whole process. What that does is increases the capacity of this $250 million plant because it frees up. If you shorten the bottleneck process, it creates additional capacity of that plant. And that's just more dollars, more revenue for the same investment. So imagine just a column being able to give you that much more capacity and revenue producing capability out of your plant, right? Very important for CMOs, right? You want your project done faster so that you can do more in the same plant. So there's a lactoferrin process that we talked about, and there are many FAQs, how the flow goes through the column, Can there be channeling in the column? How do you know if there's channeling in the column? Like anything else, if your asymmetry is off, probably have channeling in your column. So you pack some more resin or you stabilize your bed. And for using radial flow columns, do I have to use somebody's specific resin or use our systems? No. You can use anyone's resins. You can use anyone's systems. Stick with what you have. But if you want, if you are looking to upgrade, the flow capacities and the skids, we certainly can support you in that. Or if you're looking for certain ion exchange resins, we can support you with that. Because there are a whole plethora of instruments that we make. You can use anyone's machines to run our radial flow columns, but we make a whole plethora from bench to large scale, very unique, exciting technology that I'm not going to address here today because that's not the purpose of this talk, but we can support you with that. If you're using pre-packed columns of ours and want to use single-use systems with disposable flow paths, pre-sterilized flow paths, we have those machines as well. If you want to use our radial flow columns in continuous processing, whether 2 or 3 column processes, we have continuous systems as well, bench scale, large scale, single use, multi-use. Of course, I told you we've used these and then we can customize your processes and integrate various steps. So we have engineering folks here, manufacturing folks, software team. We do a lot of customized DSP projects here. And then we have our own manufacturing and automation fabrication facilities. And everything is to the standards of the biotech industry, whether it's ASME PPE, USB grade 6 material for elastomers, 316 stainless steel, electropolished, the right RA finish, full turnover package, IQ, FAT, all that stuff, right, that we provide. And so it's a very important tool in debottlenecking downstream processing. And it's one of the first ones that we feel you should address. So with that, I will conclude our talk. We are approaching the end of the hour. And so I'm going to complete this conversation and open myself for any questions that you might have. And I wanted to thank you for listening, for being, a good audience here. And we are having these sessions, seven webinars, on different topics. And please join us for other ones. If you have questions and wish to engage with us, happy to sign CDAs and have a one-on-one discussion about your particular needs, your problems, and how we can assist and solve those for you. Okay? So, so if there are no more questions, I'd like to thank you for being a great audience, for joining us this morning, and have a great rest of your day. Take care. Bye-bye.